Hi, I want to look today at what are the forces on a rider in a car, like when you're at the crest of a hill or when you're at the bottom of a hill. You've all experienced this before, or on a roller coaster it's the same kind of thing where you feel different amounts of force pushing you upwards, the seat pushing you upwards different amounts, whether you're at the top of the hill, whether you're bottom of the hill, and so on. So I'd like to work that out today, where I want to imagine a car driving first over a hill, then the bottom of a hill, where that car is going to go a constant speed just to keep our work as simple as possible. So let's imagine that the car is on cruise control or whatever. So the car is going to always be going a steady 10 meters per second, uphill, downhill, etc. And I want to think about what happens to the normal force on an 80 kilogram person. So 80 kilograms is like 170 some pounds, so that's a pretty normal mass. So looking at the normal force on an 80 kilogram person, first of all, just thinking conceptually about the question before I actually try to do any math, thinking at the top of a hill, I usually feel lighter. As I go over the crest of the hill, I feel lighter. And the reason why I feel lighter is because the seat's not pushing up on me as hard as it normally is. On the other hand, when I'm at the bottom of the hill, then that's when the seat pushes up on me even harder than I'm used to. And you can notice that effect even more so on a roller coaster. When you're at the bottom of a hill, the seat's definitely pushing you a lot harder, and at the top of a hill, it's pushing you a lot less. That's a very noticeable difference there. But before we can answer this question of what is the normal force of the seat pushing up on you, then we need some more specific details, specifically how big of an arc is that curve. So I'm going to say that each of those curves has, each of those hills is a 20-meter radius. Now, it would be pretty reasonable of you to say, wait a minute, a real hill isn't actually a circle, so that's kind of crazy talk to pretend that the hill is circular. But when I say, like, at the top of the hill, the radius of the curve is, I'm going to say it's 20 meters. What I mean is, like, if we took this hill right here, if we extended it like so, where I didn't do that very well, but hopefully you get the idea, where right here, the arc of a circle matches up with the arc of the hill, then this would be a 20-meter radius. Or looking over here to say that it's a 20-meter radius curve, then I'm talking about like this arc here. If I extended it out, then that arc would have a radius of 20 meters. So when I say that the hill here or the hill here has a radius of 20 meters, I'm not really trying to pretend that these hills are actually circles. It's just that that is how curved the surface of the hill is at this point, at that point. So I am going to work with a 20-meter radius hill, but my picture's a little bit too cluttered right now, so there. And again, in each case, we're going 10 meters per second. And the radius of each hill is 20 meters, and the mass of the rider that we're paying attention to is 80 kilograms. So the first thing that I want to do, like always, is I'm going to make a free body diagram. Now, first I'm just going to worry about what's my answer for at the top of the hill. And if I make a free body diagram at the top of the hill, then I know that on the person, there's going to be gravity down, and I calculate that by multiplying mass times little g, and there's going to be a normal force up. Now, just from thinking about this in advance, I expect that the normal force is going to be smaller than the weight, just because of my own personal experience, like I said before, that when I'm at the top of the hill, then the seat doesn't push me up as hard as it normally does. And normally, if I'm on a flat road, I would expect these two arrows to be equal. So I would expect this arrow to be a little bit smaller. And also, if you look at these two arrows, gravity down, normal force up, then that shows that there is some kind of net force that has to be downwards. Longer arrow minus this shorter arrow gives me a net force downwards. And that does make sense to me because right after the car is here, it's definitely going to curve down. So the downwards arrow has to be more than the upwards arrow. So now that I've got my free body diagram done, I'm going to write out Newton's second law. And Newton's second law still is that the total of all the forces on that object is equal to mass times acceleration. Now, I'm not interested in this car speeding up or slowing down. I'm not interested in forces this way or this way. I know if the car's on cruise control going at a constant speed that those forces this way and this way are going to add up to zero anyhow. So I'm just worried about the up and down forces, and those forces are going to cause not a change in speed, they're just going to cause a change in direction. Now, before I go any further though, I'm going to write down my net force from the diagram, but before I do that I need to think about my positive direction. And I'm going to make a different way of choosing my positive direction than you're used to. What I'm going to do for this first question is I'm going to make my positive direction be downwards. And the reason why I'm choosing that is that I want a positive acceleration. I know that the direction of acceleration is going to be downwards. So if I made my positive direction up, then I would have to remember to stick a negative sign here in front of this acceleration. And my own personal experience is I forget sometimes. And so I've just started doing the pattern always of, well, I'm going to make the direction towards the center of the circle. I'm going to make that be my positive direction, because then I'm going to have a positive acceleration, and I don't have to worry about forgetting that negative sign for the acceleration. So I'm going to make down my positive direction, so the net force is this one minus this one. So the net force is the weight of the person minus the normal force on the person is equal to the mass of the person times the acceleration of the person. And since we're not changing speed, just changing direction, that's how we know that the acceleration is speed squared divided by radius. And again, I know that this is a positive acceleration because I made it so. And I fear I make that mistake when I don't do it this way. I don't want to forget that negative sign here, so I'm just making towards the center of the circle is my positive direction because that is the direction of the acceleration. So now I've got this equation here. Now, if I'm going to put some numbers in here, the weight of the person, 80 kilograms times 9.8 meters per second squared, is 784 newtons, minus the normal force equals 80 kilograms times the speed is 10 meters per second. When I square that, 10 meters per second squared is 100 meters squared over second squared, divided by the radius I said was 20 meters. Now, when I work this out, conveniently this is math I can even do in my head. 100 divided by 20 is 5, and that's going to be meters over second squared. 5 meters over second squared is the acceleration. 5 times 80 gives me 400 newtons. So what this is telling me now is that the net force on the person driving the car is 400 newtons. But they're 784 newtons down, unknown number from the normal force up, to give me a net of 400. So if I wanted to solve for the normal force, well, I can add this over to the other side and subtract the 400 over, and I get that the normal force is 384 newtons. Now, this answer makes sense to me. And the reason why it makes sense to me is that I knew before I ever worked anything out, oh, when I'm at the top of the hill, I feel extra light because the seat's not pushing me as hard. And so if the seat's not pushing me as hard, then I've got to have, as hard as normal that is, then I've got to have a smaller normal force than I would usually have. So it should be smaller than 784, and that does work out. So hooray for that. Now let's think about what happens at the bottom of the hill. At the bottom of the hill, I'm going to use a different color here, just so I don't confuse my two bits of work. But at the bottom of the hill, I've got the exact same gravitational force, mass times little g. That's going to be 784 newtons again, nothing different there. And if I were good, then this arrow would be exactly the same length as that arrow. But now, what's happening here conceptually before I do any work? What's happening here is that this car is about to curve upwards. And so the acceleration here has to be towards the center of that circle. The acceleration has to be upwards. And so the only way that the acceleration can be upwards is if that normal force now, oh, that's going to have to be big. The normal force is going to have to be more than the weight of the person. So I've got a big normal force upwards. And using the same kind of reasoning as I did on the first question, if I want to think about my positive direction being towards the center of the circle, well, now I'm actually going to choose up as my positive direction. Again, it's just because I don't want to make mistakes about negative signs, and I know that about myself, that I'm pretty likely to make a negative sign error if I don't do it this way. So I'm just choosing towards the center of the circle as my positive direction. So I'm changing positive direction from the question that I've already answered. So again, the net force then, the net force is going to be, if my positive direction is upwards, then it's going to be the normal force minus the weight. So now, net force equals mass times acceleration. Net force, subtract these two, equals mass times the acceleration is speed squared divided by radius again. Now if I put in these things that I know, normal force is what I'm looking for, the weight is 784 newtons, equals, now it's still a 20-meter radius curve, so I'm still looking at 80 kilograms times 10 meters per second squared divided by 20 meters. It's going to be the exact same numbers as I had on the previous question. And so when I do that, 80 times 10 squared divided by 20, then that is going to give me 400 newtons again for my net force. Although this time the net force is directed up instead of directed down. So now, oh, what this is telling me is that the normal force has to be bigger than the weight by 400 newtons. So if I add that weight back over to the other side, then I get a normal force of 1,184 newtons. Now, for a person that weighs 784 newtons, to feel a normal force that's larger than that, then that matches up with the sensation that I just know from my own personal experience. And so, key points for what I'm doing here that might be different from what we've done before is I'm making choices about my positive direction based on which way is towards the center of the circle. Also, in this situation, I've got more than one force in that direction.
So Brown, please come to the